So, a little change of topics. I would like to speak about the title suggests as causality methods in time series analysis. This is what I'm looking for. So let's start a little wider perspective, and let's speak about what are the approaches to represent the world. And in the ancient times, every task was done by humans. So we did the observation, the modeling, and the solving of the models. Let's say after the starting of the science. But soon the observation was not enough, or human observation was not enough, and we used the tools for observation. And so after that, we used the observation data for our models for the solution of the models. And as time was going on, computers appeared, and now we don't have to solve the model ourselves, or just in a restricted sense, because we have computational tools. So we use the data, we do the model, but solve it with the computer. And as part of the AI is also that AI is part of this thing as well. Then we try to solve a differential equation, for example, with AI tools like the physics-informed neural networks. But nowadays, it seems to be that the future is that we don't ourselves do the modeling as well, but the AI does the modeling. So this is the data-driven approach. When we just observe the data or provide the data for the computers does the modeling and does the solution. So humans know that there is no human interaction at all in this process. So what remains as a human role, after all, of representing the world? And there are two ways which remain for us. The first is that we still have the freedom of decision. So if we haven't we learned the consequences of the data, we can determine what we'll do with that. So far, maybe it will be. So again, it can also be come out from the human perspective. But anyhow, it's today. But maybe more importantly, for the more important topic, is that we still have to understand the basic motivations that lead to the actual model, because we have to build up a good structure for the artificial intelligence. We have to use the symmetries and the relations in the model to build up an effective model for the AI. What kind of symmetries I think about? For example, there is the translation invariance. It can be a translation invariance in the incoming data, like in the case of image recognition, which leads to the CNN, the convolution neural network, which means that we use the same information in any part of the data. And so there is a convolution kernel, which goes. So that's why we need the CNN, because there is a translation and invariance in the data. There can be a scale invariance in the data, like also in image recognition. For example, if you want to recognize a traffic table, a traffic sign, then it can be anywhere in the picture and in any size. So there is a translational and a scale invariance. And that's why for image recognition, it is advantageous to have a deep network with pooling, which means that we reveal all of the structures in different scales, layer after layer. The third thing, which has a well-known symmetries, is that in a lot of cases we have a Markovian system for like in dynamical cases. That means only the latest data are relevant for us. For example, in differential equation. And then we know that for the network we build, we must use the latest data, like for example in weather forecasting. But what happens if there is no evident symmetry in the system? For example, let me say something. For example, in economics, like in stock price data, there is no, if there are a lot of firms in the stock market, it is absolutely not evident that which firm, which company affects the other. So what is the model I have to build up? And the data is not too lot. So in case of financial data, the data are very sparse. Or the other thing is that the EEG, the human brain examination, where we have a very lot of channels, and it is absolutely not evident which channel influences the other. So it is not in these cases when there is no evident symmetry, we have to do something. But this is about what I want to talk about. What can we do? The first thing is, of course, we assume a general model. So we assume that everything influences everything else, but it's actually not a good solution, because it leads to a very complicated model with a lot of parameters, and usually we don't have enough data to refine all the details, and usually it leads to a bad performance. So it's not the solution. The second one, which is an ingenious solution by Google in the attention mechanism, which in the case of language, where it's again, for the language, not just a recent history which matters, all of the history can matter. So then this attention mechanism would have a understanding which part of the earlier text influences the current context. And what I want to speak about is a more generic strategy which based on revealing causal relations. But what is causality? In very simply, causality is it's the fact that a change in a particular data channel implies a change in another channel. Like if there is a rain, we have a wet street, for example. The one channel is the rain, and the other is the wetness of the street, and there is a one correspondence from one to other. And there are different possible causal relations. So let's think that X and Y are two subsystems, and how they can be related. They can be independent. Any change in X doesn't influence any change in the Y. That's the most real thing. It can be that X drives Y. For example, that rain drives the wet street. If there is a rain, there must be the street must be, or in a lot of cases, most of the cases, the street will be rainy. So then X drives Y. That means that changes in X imply changes in Y. There can be a bidirectional relation that X drives Y and Y drives X. For example, if we have a two-component differential equation, X dot is Y, Y dot is minus X, that is a circle, then it means that X and Y are not independent channels. There are interdependent channels that are part of the same system. And then the most interesting thing, an interesting case, is that the common pose that there exists a Z, that Z drives X and Z drives Y, but X and Y are not in direct connection. And that's maybe the most intriguing case in causality. And of course, there are some combinations that are logically impossible or it's not allowed. For example, if there is a Z, that Z drives X, and we know that X drives Y, then Z is hidden. So it's just auxiliary thing. We can think that there exists a Z, but in fact, there is no logically, it is not a good solution. But anyhow, so these are the basic cases, the basic causal relations. And if we can find, let's assume that we have a multi-channel data, and if we can find that X, there's one channel drives another, then we should build a model which incorporates X and the future of Y, but not vice versa. And if we find out that there are data channels that are independent, we must say that there is no connection between them. So this is why it is important. Causality is important in building models. Okay, what kind of causality methods are there? The most known thing is the Wiener-Granger causality, which assumes, I don't want to go into more very much detail, just to mention these existing methods. This assumes that there is a linear stochastic model between the data and tries to represent the future of, say that is X and the Y channels, try to represent the future of X without incorporating the Y, the history of Y, and with incorporating the history of Y. And if there is a significant difference between the two, then we can decide that, whether or not Y drives or X. It's a very popular method, in particular in finance, in economics. So it's used to say that it's agreed to present predictive precedence, not really causal relations, and there are problems. So that, for example, a common cause cannot be very nicely shown by this method, but it is a very effective thing, very popular and very used in a lot of applications. To overcome the difficulty of that, it assumes a linear relation, the Sugihara construction, the convergent cross-mapping, it was introduced. But while the previous one, the Granger's causality works in stochastic models, the convergent cross-mapping is working on the deterministic systems. And based on the Tarken's theorem, which is the space vector construction theorem, mathematics theorem, which practically means that if we have an embedding of the data series, so we take the elements of the history, some k elements of the history, then the topology in this embedded system is the same as the topology of the attractor in the dynamic system. Anyhow, this is just a subtlety in this case. So the thing is similar, or the logic is similar. We can try to predict Y exactly from the history of X, assuming that if X drives Y, then X has some information about Y, the history of Y. Okay, and as I've said, it works in deterministic cases, and again, the detecting of common cause is somewhat heuristic. There is a recent model introduced by colleagues in Wigner, András Tercs and collaborators. And the idea, this is dimensional causality. The idea is that if X drives the Y, the dimension of the attractor in Y is larger than the attractor of X, since it contains information from X. So that's the strategy is to study the dimension of X, Y, and XY. And compares the dimensions, and from the dimensions, we can draw some consequences about the causal relations. I will, okay, so it's a relatively new method. But it also works for the deterministic cases. So our idea was that we should work out a system which works both in the stochastic and the deterministic case, and somehow uses the idea of dimensionality, so information, amount of information necessary to reconstruct a data series. How it goes. So let's think that we have a kth order differential or differential equations of a recursion, a kth order recursion, and then in this case, so this is the no, it's too faint for me. So we use this recursion here that, okay, that's nice. That describes the data, the series. But in order to start this thing, we have to fix the initial conditions. In this case, there is k initial conditions. In a kth order differential equations, there is k initial conditions we are required. So for some sense, but if we have, and if we know the recursion, and if we know the initial conditions, all of the future is fixed. Okay, so that means that the amount of information in deterministic cases equals the number of necessary initial conditions. And let's call it degrees of freedom. Now, what kind of causal relation can we read out from the degrees of freedom? So let's assume that X drives Y. What does it mean in a recursion sense? That means that X is autonomous, and means the future of X depends only on X, but the future of Y depends on X and Y. And that's why that means that for the future of X, it's not necessary, sufficient to fix the initial conditions for Y, because it is influenced by X as well. That means that we need X and Y initial conditions to determine the future of Y. And that's why the degrees of freedom of Y is larger than the degrees of freedom of X. And this is the basic thought we can use and elaborate in this method. In the similar way, if X drives Y and so there's a bidirectional connections, then the necessary initial conditions are the same for the both. Okay, and what if there is a common cause? That means maybe it is not unobserved thing. So maybe Z is unobserved, but still we can conclude that there is a common cause, because if we understand that it's a necessary initial conditions for X and necessary initial conditions on Y, and the necessary initial conditions for the composite systems, I mean X and Y together, and X and Y together requires less initial conditions than X plus Y. And that means that we can uniquely conclude that there is a common cause in this case. So let's, these are the consequences of what I've thought, what I've told, is that if X drives Y, then the degrees of freedom of X is smaller than Y. If there is a bidirectional connection, then the X and Y degrees of freedom are the same. And if there is a common cause, then the degrees of freedom of X and Y, the sum of them is smaller than the XY system, the composite system. So only one thing has remained, but how do we determine the initial conditions in a data-driven way? So if we only see the data, and how it can be applied for the stochastic system. So how can we determine the degrees of freedom? But what does it mean? Degrees of freedom means the number of initial conditions. So the question is, what comes after a certain fixed series? What can come after fixing some values in the past? So if the number of fixed values is larger than the degrees of freedom, there is just a unique value which is allowed, or zero or one, because it is determined already. The complete series is determined. So all of the future fixed value is just a single one. It's fixed. If A is smaller than the degree of freedom, there is a distribution of the allowed values. So a lot of values are allowed, and depending on how we choose the other unfixed part of the initial conditions, it can lead to some bit probability distribution. So that means that fixing the past and looking for the distribution of the future values is uniquely in a one-to-one correspondence with the degrees of freedom. And it is true for stochastic case. In the stochastic case, after fixing the numbers, the values in the past, doesn't uniquely fix the future, but if we incorporate more and more information from the past, it will narrower and narrower, and after a while, it stabilizes. And then we know that we reached the maximal amount of information which can come from the past, and which leads, even in stochastic case, the notion of degree of freedom. Okay, now we have okay, let's go. How many time do I have? 6 minutes, I think. So how can we do it? So let's assume we have a data series, and let's filter it according to some condition posed on the generic item in the data series, which usually we use it a window. So we allow data or the values in a given data window. This is our condition, which restricts the allowed data series, so posed on a generic n position. Of course, if we okay, let's start with that thing. If the window is too large, then all of the values are allowed. So this is not a restriction. If the W is the window size is infinity, then any value is allowed, and there is no information. So this is one hand, no information. On the other hand, if W is the window is too small, then probably we don't have any data which satisfies that condition. So that is okay. There is a lot of information, but no statistics. So there is a trade-off between information and statistics in these cases, and a physicist solution for that case is finite size scaling. So let's have a scan with W, and let's look how it looks like, how it behaves, this curve, and try to draw some information from that. Okay. What is this? Okay, yeah, it's a generic thing. So just a remark that okay, so those I've spoken about. So there is an interesting thing which is a philosophical part, so to say. So of course, in the real world, everything affects everything. So the position of Mars will affect the functioning of this projector, for some in a very, very, very tiny way. But if we have a infinitely precise measurement, then everything will interact with everything else. Okay. So that means that the number of degree of freedom is not a God-given thing. It depends on the accuracy. So there is a hidden other scaling factor in this case. This is the accuracy. This is the renormalization group scale, so to say, in a physicist language. So we have to aware of this thing. Now let's have some examples. Let's have we have chosen a system which is analytically tractable, so there is analytic results in these cases. We have three subsystems which are linearly connected and a stochastic system. And there is Z is autonomous, and it's a common force for X and Y. And the question is, how can we see it in data? Just seeing the data without knowing the dynamics of the system. So this is the Z subsystem. If we constrain the Z, the possible values of the Z, and look at the future of the Z, this is what we see. If we don't constrain at all, then this is the case, of course. There is no constraint. The W is large. But if we apply just one condition from the past, it's a first order recursion in these cases. If we just fix the one past value, then it will be 0. But of course, since we just have a window size, but shrinking the window size leads to the 0. So in the log-log scale, it leads to a linearly decreasing line, which goes to minus infinity. So this is how we can reveal that there is no information remained in the past. What is in the stochastic case? For a certain period, the information is we get more and more information, but after a while, which is determined by the level of stochasticity, in this case, it will saturate. So this is the level of the noise in the system. Okay, let's go on, and let's see what happens if we look at the X subsystem, and we see that for the degrees of, without seeing the Z, we can still have, we know that without fixing anything, this is okay, that nothing happens. With fixing one condition in the past, it will decrease, the information is increasing, so the precision is decreasing, variance is decreasing in this case, but saturates in a non-zero level. And just after fixing the two necessary initial conditions, we'll go to the very, very sharp distribution. And in this case, the stochastic case is very instructive because there is a system level, system noise, And this is the degree of freedom which we observe. If the system noise is larger than the degree of freedom, then we do not see that degree of freedom. We don't then think that it is a first order recursion. But it's, as I've said, it's not a bug, it's a feature, because it's like the effect of Mars on the projector. The projector depends on so lot of information that the effect of Mars cannot be worked out, cannot be seen. There are other cases. I don't go into details. This is when I fix, I constrain the X and look at the Y. And in vain do we fix more and more past values of X. The Y won't go to a sharp distribution because there is information which I cannot fix by fixing the value of the history of X, because Z and X and Y are in some sense independent. And just the last one about slide is just this is a usual benchmark data for the causality systems. This is the chicken and egg data, which depends on the data comes from the U.S. Department of Agriculture in this period, and the question is that which was before chicken or egg. And from this data, we see that if we constrain the egg data, the chicken data are constrained. But if we constrain chicken data, the egg data are not constrained at all. So we can conclude that egg drives chicken, but of course, this is not a scientific consequence, just an economic thing. Okay, this is the conclusion, and I don't want to read it. So thank you for your attention.
Thank you, Tony. Any questions or comments? Yes, Vera.
Thanks. So your last slide was about an example, and this is what I wanted to ask, actually, a little bit more practical example. Are you using that? You mentioned at some point financial business or anything?
This thing is, of course. This was in our paper. So this is the classical benchmarking for closure system, which I tried, actually. I used the weather data, Hungarian weather data. And there is this saying that if Katalin is Katalin kopog, karácsony locsog, so if Katalin is cold and Christmas is mild, and vice versa. And one can check it with causality methods, and it turns out to be true. So not only in the Christmas time, in all of every day in the year. So if we have an unusually cold period of time say in a week, then after a month, so after 4 weeks, with a good confidence level, there is a drawback, a backfiring. So the weather will be unusually milder. So it's a 4-week period, probably because of the movement of the cyclones. I don't know exactly the reason, but it is a statistical or a fact that can be checked in weather. So that's why I say that if we have a multi-channel, a very, very complicated system, this is the first and very, very simple tool to look at the data. That whether or not there can be expected some connections, which maybe we don't have than just building the model.
Coming back to this example, then the problem here is that it's quite a huge time delay. So you have 4 weeks, right?
Yes.
That means you have to check a lot of variables among them, and it is only once in a year.
No, it's not a single year. It's a statistics of years. And the point here is that you just collect all the data for the year to year. So there is a database of data, and you fix one day in this case, and just read out all of the other day. You don't have to solve anything. Just fix. So you filter out the amount of data you have with the conditions that say in 1st of January there is a mild weather, and just read out all of the data and just determine the mean. And it is so simple. You don't need model. You don't need any assumption. Just okay. This is the strength of this method.
If you have to consider a lot of explaining variables,
No, you don't.
Then you are lost in the.
No, you
in the
don't
maths.
have to assume anything. You just fix the data at a given time. If you filter the data series with a condition, and just look at the mean of the or the variance of the later data, and it's absolutely no parameters in this case. Nothing. Just
I mean, if you have to check a month period,
yeah,
you already have to have 30 dates, 30 parameters.
but
And
it's
one will come out true, yes?
no.
But that means that you are introducing a lot of noise in your analysis.
Once again, so what I do is that collect all the data. Just single out, let's first I determine the mean of the data unconstrained. Then second, I filter out data, all of the data sets data with the conditions that 1st of January is mine. This is just one thing. And then again, determine the mean of all of the other data. There is no parameters here. Just a single, okay.
Okay, so
Maybe.
let's continue it
Okay,
later. Any other questions? No, let's thank the speaker again.